This video is an introduction to cloud overlay networks focusing on VXLAN as the tunneling protocol. It will start with a brief analogy to describe an overlay network. Then it will look at some issues in the cloud and how an overlay network can resolve them. Next I will show a packet walkthrough to describe how the overlay network is implemented. This will include a look at a Wireshark capture of VXLAN packets. I've also posted a follow-up video, VXLAN overlay networks with Open vSwitch. In that video I show lab implementation details of creating VXLAN tunnels between Open vSwitch instances. Let's start with a quick analogy for an overlay network. This analogy may seem a little funny, but it is very brief and I think a useful starting point. Imagine there are two castles. One castle is in the west and one is in the east. These castles are separated from each other by some land that can't be crossed by foot. Let's say the king in the west castle needs to send an urgent message to the king of the east castle. How can he do this? Perhaps these kings have access to messenger pigeons. So King Rest writes his message, folds it up, puts it in an envelope, and ties it to a pigeon. The pigeon flies over the land to the east castle. At the east castle, King East gets this envelope from the pigeon, opens it up, and reads it. You could visualize this as though there is a virtual link between King West and King East. The key for their communication is they have this transport mechanism, a pigeon that can fly over the land, carrying encapsulated messages between them. So here is a stripped-down cloud network topology to match this idea. In the cloud, there are virtual machines located on separate physical servers. Through a tunneling mechanism like VXLAN, an overlay virtual network can be created. The overlay network makes it appear to the VMs as if they have a direct Layer 2 connection to one another. Messages can pass between VMs through these tunnels without the VMs having any awareness of the network infrastructure in between, or the tunneling mechanism in place. Underlay network. Now let's look more specifically at how this might look in a real network. This network has two routers separating two Layer 2 rack switches. For this example, there are only two subnets, 192.168.1.0/24 on the left side and 192.168.2.0/24 on the right side. Since there will be an overlay network on top of this network infrastructure seen here is often referred to as the underlay network. Then there are two physical servers. Server 1 on the left is assigned an IP address 192.168.1.10. Server 2 on the right is assigned 192.168.2.20. These servers will have some hypervisor installed on them, for example KVM, ESXi, or Xen. For this example, the servers will also have virtual switches on them for VM network connectivity. Tenants. Now there is the first tenant of this cloud. This tenant will be called the red tenant. This tenant turns up their first virtual machine, and a cloud orchestration platform like OpenStack perhaps places this VM over on server 1. This VM is named Red 1. The tenant assigns IP 10.0.0.1 to Red 1. Then the red tenant turns up a second VM, Red 2, which is spun up over on server 2. For Red 2, the tenant assigns IP 10.0.0.2. Now we can pause and already see some issues. Our network infrastructure or underlay network has no routing knowledge of these IP addresses 10.0.0.1 and 10.0.0.2 of Red 1 and Red 2. It is only aware of the 192.168.1.0 and 2.0 subnets. In addition to this, there is not even a Layer 2 connection between the VMs. There are routers creating a Layer 3 boundary between the VMs. Before looking at how tunneling can resolve this, let's add another tenant and get an idea of some of the issues multi-tenancy introduces. This second tenant is the blue tenant. The blue tenant turns up two VMs as well, Blue 1 and Blue 2. Coincidentally, the blue tenant also wants to use IP addresses 10.0.0.1 and .2. Now we see the need to have a logical separation of tenants. Each tenant is expecting their own isolated virtual networks. They require a logical separation so they have flexibility of IP addressing, and of course for security so no other tenant can see their private traffic. There are also concerns about scalability. Traditional 802.1q VLANs support only 4,096 TACs, which is an insufficient number for large cloud deployments. Additionally, in the cloud, there can be a very large number of virtual machines. This has the potential to be a problem if the network infrastructure has switches with small forwarding table limits. Let's quickly summarize the highlighted issues. Tenants require Layer 2 adjacency across Layer 3 boundaries. Tenants require a logical separation of traffic between virtual networks for security and to support overlapping addressing amongst tenants. There needs to be a logical separation of virtual networks used by tenants from the physical underlay network. Support is needed for many virtual networks, more than the 4,000 that traditional 802.1q VLANs permit. forwarding tables are getting large due to the high number of virtual machines. Overlay network. Now let's see how an overlay network can handle these issues. For this example, I'll show virtual switches as virtual network endpoints and VXLAN for the tunneling mechanism. Keep in mind there are other solutions for tunneling. For example, hypervisors could be the virtual network endpoints, and other tunneling protocols like Network Virtualization GRE or NVGRE could be used. With tunneling, the requirement for the underlay network is only that there is IP connectivity between physical servers. So in this example, that means server 1 with an IP of 192.168.1.10 can reach 192.168.2.20 on server 2. With this assumption, the details of the underlay network can be abstracted away. VTEP learning. Again, the virtual switches will act as virtual network endpoints. In VXLAN, this is called VTEPs, or virtual tunnel endpoints. The VTEPs need to know where VMs are located for each tenant. For example, the virtual switch acting as a VTEP in server 1 has to learn that to reach the red 2 VM, it needs to go through server 2 at 192.168.2.20. Likewise, the virtual switch acting as a VTEP on server 2 needs to know that to reach the red 1 VM, it needs to go through server 1 at 192.168.1.10. So this means the VTEPs or virtual switches here need to have a table mapping VM MAC addresses to virtual network endpoint IP addresses. Methods tunnel endpoints can utilize to get these mappings include manual, push, pull, and dynamic learning. Manual will be configured by hand, so that's only useful in a lab or learning environment. I actually show this method in a follow-up video, VXLAN overlay networks with Open vSwitch. VTEPs could also acquire mappings of VM MAC to tunnel endpoint IPs in a push process by something like an SDN controller. In a pull process, the VTEPs could request mapping information from a central directory. With dynamic source learning, VTEPs learn information through the flow of packets they see in the network. This is somewhat analogous to traditional layer 2 switch learning. For example, broadcast messages from VMs can be encapsulated into multicast messages to get across the network to VTEP subscribers. At the multicast destinations, VTEPs will learn from packets the mapping of source VM to source tunnel endpoint IP. Much more detail on source learning with multicast is in the VXLAN IETF draft that I'll link to in the video description. Regardless of how the virtual network endpoints learn this information, just remember again that tunnel endpoints need a mapping of VM MAC address to VTEP IPs. Now let's take a look at the tunneling of packets in the overlay network with a packet walkthrough. Packet walkthrough. Red 1 wants to send a packet to Red 2 at 10.0.0.2. For the purposes of this discussion, assume the learning discussed before and the ARP process has already completed. So Red 1 sends a packet with a destination IP and MAC of Red 2 and a source IP and MAC of Red 1. This packet is received by the VTEP in server 1. The VTEP reads this packet and sees it came from the Red tenant with the destination of Red 2's MAC address. So it does a table lookup and finds that the MAC of Red 2 is reached through 192.168.2.20. To ship this packet over to Red 2, the VTEP encapsulates the packet with new headers. Let's start with the outermost headers and work in. First there is the outer layer 2 header, which is not shown here but is dependent on layer 3 hops in the underlay network. Next there is the layer 3 outer header with a destination IP of 192.168.2.20, the VTEP on server 2. The source IP is 192.168.1.10, the VTEP of server 1. After layer 3 is a layer 4 UDP header with a destination port of 4789, which has been reserved by the Internet Assigned Numbers Authority for VXLAN. The source UDP port is dynamically calculated, preferably based on a hash of the inner packet. The source port being dynamically calculated is actually very important for load balancing. This creates variability in the source UDP ports for packets between pairs of VMs. This variability ensures load balancing over port channels, which often perform a hash function that includes layer 4 port numbers to pick physical ports to send traffic over. VXLAN header. Moving in on the packet, next is the VXLAN header. Recall that the blue and red tenants are using the same IP addressing. How can VTEPs distinguish tenant traffic? In VXLAN, this is accomplished by the VXLAN Network Identifier, or VNI. In this example, the red tenant's virtual network is assigned VNI 100. This VNI is analogous to a traditional VLAN tag. However, with VXLAN there is much more scalability. As noted before, 802.1q traditional VLANs support only 4096 combinations, due to having 12 bits reserved for their use. VNIs, however, have 24 bits reserved, which allows for over 16 million VXLAN identifiers. After the VXLAN header, there is the original packet from Red 1. With the outer headers in place, the packet reaches the VTEP on server 2 at 192.168.2.20. This VTEP receives this VXLAN packet and reads off the VNI of 100 reserved for the red tenant. The VTEP then strips off all the outer headers, leaving the original packet from Red 1 to Red 2. This packet is forwarded to Red 2. Red 2 has no knowledge of the VXLAN-based encapsulation that was required to get this packet to it. Let's review this by looking at it quickly in reverse. Red 2 sends its reply to Red 1. Red 2 puts a packet out on its virtual interface with a destination of 10.0.0.1 and a source of 10.0.0.2. The VTEP on server 2 encapsulates this packet with new outer headers at layers 2, 3, 4, as well as the VXLAN header. Layer 2 on the outer header is used to reach the next hop device in the underlay network. Layer 3 on the outer header has a destination IP of the VTEP at server 1, 192.168.1.10, and a source of 192.168.2.20. Layer 4 has a destination port of 4789, as well as a dynamic UDP source port. In the VXLAN header, there is also a VNI with a tag of 100, which identifies one of the red tenant's virtual networks. The underlay network only looks at the outer headers, so it gets this VXLAN packet over to the VTEP on server 1. There the outer headers are stripped, and the original packet from Red 2 is forwarded on to Red 1, again with the VMs having no knowledge of the encapsulation process required. For the blue tenant, things will look almost exactly the same since the blue tenant is using the same IP addressing as the red tenant. The critical difference, however, is the blue tenant is assigned a different VNI, in this example VNI 200. Through VNIs, traffic is logically separated. So in the end, we can abstract this as a pseudo-link between the VMs, much like the virtual link between castles created by our messenger pigeon in the earlier analogy. In the analogy, the transport mechanism was the pigeon. In this cloud, the transport mechanism is VXLAN encapsulation. Packet capture. Finally, I want to wrap up by looking at a Wireshark capture of VXLAN tunneled packets. Here I have opened a Wireshark capture of some VXLAN encapsulated traffic. I'm filtering on UDP port 4789, which is reserved for VXLAN. This doesn't look quite right yet. That's because I need to let Wireshark know these are VXLAN packets. I'll right-click on one of the packets and select Decode As. Here I want to select all 4789 port traffic, and in this window I want to select VXLAN and hit OK. Now we can see the VXLAN packets clearly. In the packet list window on top, Wireshark is not even showing the details of the VXLAN headers. We just see the packets that are being tunneled. Here is a ping request from Red 1 to Red 2. In the Wireshark packet details window, we can see the full packet. Above this line are the VXLAN encapsulation headers, and below it is the original packet from Red 1. The outer IP layer shows the destination IP of server 2 at 192.168.2.20. The source IP is server 1 at 192.168.1.10. Here is the UDP header with the destination UDP port of 4789 and the dynamic source UDP port. Then there is the VXLAN header. If we expand this, we can see that the VNI is set to 100. After the VXLAN encapsulation headers is the original ICMP message from Red 1 to Red 2. This is all Red 2 will see. Red 2 is unaware of the encapsulation that occurs. Moving down, we can find a ping request from Blue 1 to Blue 2. This packet is really the same as the one just shown, with one key exception. The VNI, which in this case is now 200. So the VNIs again are how there is a logical separation between the blue and the red tenant, and how the two tenants can be using the same IP and MAC addresses. That's it for this look at overlay networks focusing on VXLAN. If you found this video helpful and would like to see more videos on SDN and network virtualization, as well as traditional networking topics, please subscribe to this channel. In the follow-up video, VXLAN Overlay Networks with Open vSwitch, I demo some actual lab work using VXLAN tunneling with Open vSwitch. I can be contacted via LinkedIn at linkedin.com/in/David Mahler. Thanks to those who have contacted me there already and said hello. In the video description, I'll include links to references for this video, including the IETF Networking Virtualization Overlays Working Group, NVO3, and the IETF VXLAN draft. Also some great networking blogs, including one from Derek Chamorro at therandomsecurity.com, which has a great VXLAN post. Also the well-known network static blog from Brent Salisbury, with an entry on VXLAN tunneling and overlay networks. Thanks for watching.